Hello friend, welcome to the electric neuron. I am here with taking another interesting video lecture that is based on the inductance of double conductor. So we have previously seen the transposition of the three-phase line of the distribution and transmission system. So today we are going to see about the inductance of bundle conductor. So first let us know why we are use the bundle conductor. What are the purposes of use this bundle instead of a single? So because of the hour, it is very economical to large and chunk of power over a long distance by employing the EHV, that is extra high voltage line. By employing extra high voltage line, EHV line, however the line voltage that is can be used are severely limited by the phenomena of, that is, corona. Okay, so because it is economical to transmit large chunk of power over the long distance by lumping or employing extra high voltage line, however this voltage can be severely limited to the phenomenon of corona. So the corona effect occur here. Due to this we are using our double conductor. So corona can be raised or raised considerably by the use of double conductor. So corona is the fact in which it ionizes the atmosphere. What does it do? Ionize. First ionize and then produced hissing noise. HIZING, hissing noise with production of ozone gas. It produced ozone gas. So corona discharge caused communication interference. It caused communication interference. Remember that corona discharge caused the communication interference and associated power loss, which can be severe in bad weather condition, and critical line voltage for formation of corona can be here raised in the bundle conductor. So this increase in the critical corona voltage is depend on the number of conductor in the group, and that will be clearance between and the distance between the group forming separate phases. So in the next slide we have to see all the type of bundle conductor. Let's see here. In the there is two conductor. Let this is one conductor and this is one conductor placed over a distance d, and this is called our bundle conductor. So by increasing our self GMD here, by increasing our self GMD, the inductance will be decreased considerably with incidental advantages of increment transmission capacity in the line. So let's first see the GMR, that is geometric mean radius. That is GMR. GMR is equal to DSB is equal to root over of 4 ds into small d square, that is equal to root over of ds into d. So what is DSB? DSB is the geometric mean radius. GMR, geometric mean radius of this bundle conductor, and that is equal to root over of 4 ds. What is ds? ds is our geometric mean radius of each subconductor. That means geometric mean radius of that subconductor, that is ds, and geometric mean radius of that subconductor, that is ds. Okay, and what is d? D is the this distance, distance between two conductor. By converting this, we will get root over of ds into d, geometric mean radius of each subconductor into spacing between two subconductor. Okay, this is for two conductor, this formula. And then we are coming to this triple conductor or triplex. That is one conductor, that is another conductor, and that is another conductor. Let conductor phase A, conductor phase B, conductor phase C. Then they are spaced equally with distance d apart from each other. And for finding GMR, this is our formula. GMR is equal to DSB, that is geometric mean radius of this bundle conductor of 3 phases, that is equal to root over of 9 ds, that is geometric mean radius of each subconductor, and d is the distance of all those conductor, their distance, that distance, and their distance. Q to the power root over 9. By converting this, we will get this formula, root over of q ds into d square. Okay, remember all this formula that are helping you to in the your examination. These are carrying 3 to 4 mark in your examination, so it is very important to your competitive examination like SSC, railway, and GATE, and your university exam. So please take a screenshot. I think we have done. So let's going to our next slide. That is for conductor 4 conductor. That is 4 conductor means quadruplex. That is quadruplex means 4 conductor placed. Let conductor A, conductor B, conductor C, conductor D, and those conductor are equally placed by a distance d. So it is geometric mean radius is equal to dsv, and dsv is equal to root over of 16 ds into spacing distance d and spacing distance d, and then spacing distance d into root 2. Why we are taking root 2? Because of this corner point, to the power 4. By converting this, we will get 1.09 into root over 4 ds into d cube, and those specification here. dsb is the geometric mean radius of bundle conductor, and ds is the geometric mean radius of each subconductor of bundle, and d is the spacing between the subconductor of bundle. So please take a screenshot. I think you have done. Okay, so here please remember this thing. Geometric mean diameter of bundle conductor. Geometric mean diameter of bundle conductor can be found by taking root of product of distance from each conductor, that is equal to like that. If there is a conductor and there is another conductor, there is another conductor, there is another conductor, let this conductor is A, this conductor is B, this conductor is C, this conductor is D, and this is the distance d1, this is distance d2, this is distance d3. Okay, so here geometric mean distance is equal to this statement saying that root over of d1 d2 distance from A to C, d3 distance from A to D with its cube. Okay, this is your formula. And the inductance of the bundle conductor line is less than the inductance of the line with one conductor per phase. So let's see how it is. Because of the, see, in the bundle conductor our geometric mean distance is increased. Due to this, our inductance will be decreased in the bundle conductor. So this statement is saying that inductance of the bundle conductor is less. Inductance of the bundle conductor is less than the inductance of the line conductor of the phase, one phase. Okay, are you clear, guys? I think you are clear. If not clear, then ask me in the comment section. I will clear your doubt. Okay, so let's going to our inductance of double circuit three phase line. So why we are using this? To increase the transmission reliability, we use this circuit. Transmission reliability, for our reliability purposes, we are using this double circuit line of three phase, and it is desirable to build the two line with low inductance. In the previous slide we have seen that low inductance in the bundle conductor, that which increase the geometric mean diameter. But this formula only na, this formula I am writing here, inductance is equal to 2 into 10 to the power minus 7 ln d divided by r dash. R dash is your fictitious radius, and d, this is your geometric mean diameter or geometric mean distance, GMD. So by increasing this will be decreased because of this formula. Okay, from this formula we will get this relation in the previous relation here, this relation. Okay, are you clear? Okay, I think you are clear. So in order to achieve the self GMD should be high, mutual GMD should be made low. So to getting our self GMD should be high, our mutual GMD could be taken as a low, and therefore the individual conductor of the phase should be apart as possible for high self GMD, while the distance between phase kept as low as possible for low GMD. Keep remember this 3 point. Those are help you in writing the year part 2 of the SSC exam. So keep remember this. Okay, so our next slide here, this is your figure of this inductance of double circuit three phase line, double circuit three phase line. Okay, so let's see. In this it may be noted that here a bar, a and a dash, this, are you seeing, guys? This is your a, this is your a dash, this is your a dash, and this is your b, this is your b dash, this is your c, and this is your c dash, like that in section 1, section 2, section 3. Okay, there is 3 section, and this distance from this to this is d, and this distance is also d, and from a to c this distance is h, that means b to b dash the distance is h, that means c to a dash this distance is h, and the distance between b dash to a dash or a dash to c dash is p, and the c dash to b is p, and the distance between a to a dash or c to c dash or b to b dash is q. Okay, it is clear. Here all the conductors are placed in parallel manner, but in not circuit manner parallel. Okay, so here a and a dash in parallel compose of phase A, and b and b dash compose of phase B, which are in parallel, and c and c dash compose of phase B, which are in parallel. In order to achieve the ds, what is ds? Our self GMD, yes or not? Self GMD, the conductor of two phases are placed diametrically opposite to each other, and thus of the third phase are horizontally opposite to each other. So let's see, equivalent, that is equivalent diameter is equal to DAV into DVC into DCA. DAV into DVC into DCA. How it is placed? Let's see here. Let me erase first. DAV, distance between A to B, and DVC, distance between B to C, and DCA, distance between C to A. This distance to the power 1 by 3. Our formula of equivalent distance. Okay, so let's see full formula, how it is derived. So here, to find the DAV, this is our mutual GMD between phase A and B in the section 1, and that is equal to dp into dp to the power 1 by 4. How will that come? Let's see. dp into dp, so the distance between here, let me erase. Okay, the distance between A to B is what? D. And the distance between B to A is the same distance D, so D into D. And the distance between A to B dash that is P, and the distance between B dash to A, that is also P. So there is 4 distance are come in our face. Okay, so 4 distance, that means DD is D square, PP is P square. Okay, so D square and P square, and we are taking 1 by 4. Why? Because of the 4 distance, 1 by 4 to the power 1 by 4. So the square are coming to the outer side, that is 2 multiply with 2, or D into P 1 by 4 into 2. By cancelling this 2 and 4, D P to the power 1 by 2. Yes or not? So this is our formula, dp to the power 1 by 2. Like that in the B to C, distance between B to C, mutual geometric mean distance between the phase B to C in the section 1, like that in the previous DA to B. And CA, distance CA, let's see how it will be formed. Let me erase first. DC to A, so here is the distance C to A, that is H, and that A to C, that is also H, and then A to C, A dash to C, what is the distance? A dash to C, D, and then again C to A dash, what is the distance? D, not D, it is 2D. Okay, remember that it is 2D. 2D, that means 2D into 2D, 2D into 2D. I am writing here 2 into 2. Okay, so yeah, how there is 4 distance placed in our face. So we are taking 1 by 4, and by converting this h square into d square to the power 1 by 4, and by converting this we will get into 2, here 2, by taking common 2 h into d 1 by 4 into 2, that is 1 by 2. So our formula is 2hd distance to the power 1 by 2. So let's see. Yes, this is correct, 2dh to the power 1 by 2. So hence the equivalent distance or equivalent geometric mean diameter is equal to, or distance is equal to 2 into 2 to the power 1 by 6 into d to the power 1 by 2 into p to the power 1 by 3 into t to the power 1 by 6. By placing all the equation in this equation, okay, we will get this 2 to the power 1 by 6, d to the power 1 by 2, p to the power 1 by 3, and h to the power 1 by 6. Okay, So let's see the self GMD in section 1 of phase A. I conductor A to A dash. So conductor A to A dash like this in this conductor. See here, I am explaining this A to A dash. That means this distance Q and this distance again Q, A to A dash and A to A dash to A, and then the self distance, that is R dash from A dash, that is again R dash, because of the radius are same. So there is 4 distance by taking 1 by 4. So like that, Q square into R dash square to the power 1 by 4, and by taking converting this Q R to the power 1 by 2. Yes or not? I think it is correct. Let's see. Yes, this is R dash Q to the power 1 by 2. So self GMD of phase B and C, like that in the previous SV and SC, we are find that R H to the power 1 by 2 and R dash Q to the power 1 by 2. So equivalent self GMD DS is equal to DSA, DSV, DSC to the power 1 by 2. Those are our self GMD. From these 3 equation we will get this only by converting this R dash to the power 1 by 2, Q dash to the power 1 by 3, H 1 by 6. Okay, please remember all these things and take the screenshot of this. Okay, so let's see our inductance. We know the inductance, that is equal to our 2 into 10 to the power minus 7 ln D equivalent divided by ds, and that is equal to, by placing all the previous calculation here, 2 into 10 to the power minus 7 ln 2 into 2 to the power 1 by 6, d to the power 1 by 2, p to the power 1 by 3, and p to the power 1 by 6 from previous equation. See here, from this equation D equivalent will be taken. Okay, and from this equation equivalent self GMD will be taken. Okay, by placing this 2 into 10 to the power minus 7 ln 2 in 2 to the power 1 by 6 and d to the power r dash to the power 1 by 2 and into v by q to the power 1 by 3 Henry per phase per meter, because of the inductance, its unit. And the self inductance of each conductor is equal to 2 into 10 to the power minus 7 ln 2 to the power 1 by 3 into d to the power r dash. This is our self GMD, and or not self GMD, this is our self inductance L. Okay, this is our self inductance, and the mutual inductance is this one, 2 into 10 to the power minus 7 ln p divided by q 2 to the power 3. This is our self, this is our mutual. So by combining this we will get equivalent, that is L is equal to 1 by 2 Ls into M, that is 1 by 2 into self inductance plus mutual inductance. This is our mutual inductance. Okay, please take a screenshot. I think we have done. So it's complete. Thank you for watching.